Yes, hello. So I'm indeed PJ. I'm a CTO at TO. And one of the problems that I've had over the past years is I've actually watched a lot of talks on low latency. And the big problem that I always find with them is they always talk about how great solution X is. But usually all of these solutions, they're presenting numbers which are coming out of lab environments. And of course, I think we all know that if you're testing on your own laptop, you can make latency work quite well. So I wanted to do something a little bit different compared to that. I really wanted to talk about a very specific customer case that we had a while back. And for them, they really came to us with the problem, we have horrible networks and we need to push a lot of low latency video across them. So let me give you some background. The customer I'm talking about, I cannot use their name, but whatever. They're based in UK and Ireland, and they are what I would refer to as a retail betting experience. That's what they provide. Very similar to digital signage. You have big TV screens, a lot of them in bars, and there has to be video pushed towards them. Very simple setup. They have Amino set-top boxes connected to big TVs. But the problem, or at least the real problem that they're having is they are using very, very cheap consumer internet access points. And these consumer networks, they are not really great. There's a lot of weird things going on. For example, there's a lot of weird routing, something we figured out quite quickly. Yes, they are in the UK and in Ireland, but if you see where their traffic is originating, for a lot of the ISPs of the networks that they're using, it's originating in Amsterdam because they're being piggybacked over a Liberty Global backbone, which is in Amsterdam. And for some reason, it was actually faster for us, or at least better from a latency perspective, if we put the origins in mainland Europe compared to putting them in the UK, which was very, very weird. Also, as I already said, this customer was saying we have horrible network conditions in these bars. But what did it mean? It meant a lot of different things. It meant that at some points in time, all of a sudden, there was a lot of packets being dropped. And then after that, again, it was fine. Very, very much fluctuating. Also, very fluctuating bandwidth, very fluctuating round trip times. At one point in time, a few tens of milliseconds. A little bit later, same request, same origin, everything would be the same, except that round trip time was now a few hundred milliseconds. Not really convenient if you're targeting low latency. And that's actually why, at a certain point in time, they started saying that about 20% of the bars that they have, they were bad bars. But this number, it was continuously growing because whenever there was another bar and there was some kind of incident there and the network was bad at a certain point in time, they would say, this is now a bad bar as well. And it got classified into that bucket. So if this had gone on and on, I would have expected that at a certain point in time, all of their bars would have been categorized as bad bars. Now, I mentioned we're doing latency, low latency, and low latency for this customer is actually key. I mentioned retail betting as an experience. Well, for retail betting, latency, well, betting in general, actually, latency can become really, really critical. In this case, it's about doing in-stream betting, in-play betting, meaning that you want to allow your users to bet as close to the actual action that is happening as possible. Why is it important? Of course, if there's somebody at a match calling his buddy, hey, this just happened, and he can place a bet at that point in time because he hasn't seen it, there's going to be some abuse there. So you need to close your betting window at the point in time when the action really happened. So if your latency is as low as possible, people can bet as long as they can. And if they would place a bet, that bet gets rejected because it was placed too late. If that bet then actually happens, well, your audience is going to be quite annoyed about it. You'll have angry customers in your bars. You're also rejecting bets, so you're also getting less revenue out of it. Not really good. So, well, having low latency really makes a business case here. And what was this customer doing at the point in time when we came in contact with them? They were actually migrating away from an old HLS-based solution, which had a high latency, and they were moving towards a WebRTC-based solution. Simple setup, they had WebRTC servers running on AWS, 700 milliseconds of latency, and that was working fine for the first, let's say, dozen of bars that they had. But once they started scaling it out and adding more bars onto the system, they started noticing, well, they started bumping into these bad bars. So all of a sudden, there were stalls happening, there were stutters, the user experience wasn't good, things were breaking. And I actually think that they also had some kind of scalability issue, because it was even starting to break in those first 10 shops sometimes, or they just were not lucky enough to have this erratic behavior sometimes. But it didn't really work. Now, I don't know how many people have experience with the amino boxes, but they can also play an SRT feed directly. And they were feeding this WebRTC system with SRT feeds. So one of the technical guys said, but can I not just play this SRT feed on this box? They tried it, it worked, but the problem was they had to increase the buffer sizes for these SRT feeds, because otherwise it was also not getting through the network. So they started having this mixed setup. A big part of their traffic was on WebRTC, was very nice, but also a growing part of their traffic was moving towards an SRT setup with big buffers, with high latency, and with quite a high cost as well, given the way that it was set up. So they needed some kind of solution. And that's about the time when we actually got involved. So what did we do? We had been working, of course, on lower latency for quite a long time. One of the things that we've been doing over the past 8 years was working on something which we call HESP, the High Efficiency Streaming Protocol. And I will not dig into what HESP is. Most important thing to know, it's built for large-scale streaming, live streaming, mostly focused on fan engagement and user experience, low latency, fast channel change, all those kind of things, while not throwing the baby away with the bathwater, still CMAF compatible DRM. But you can always talk to me afterwards. I can talk on that for quite a long time. So if you want to get bored, come and find me after the break. And in theory, this protocol, it does all of the good things that this customer needed. But obviously, if they're saying these are the worst networks we've ever met, then we were also thinking like, will these really be the worst networks we've ever seen? Because in production, with all of our other customers, this system is running with 700, 800 milliseconds kind of end-to-end latency, which is quite good. That would absolutely be the range that this customer wants to be in. But we were, of course, thinking, what will happen? So we started, let's just give them our off-the-shelf stuff, and it had good performance in all of these good bars, but it didn't always have the right performance in these bad bars. What we saw there was there were a lot of ABR switches. Very normal. What we actually noticed was at some points in time, there were indeed very high peaks of packet loss. There were TCP windows being squeezed down. There were all kinds of different things happening. What the system then automatically does is it terminates the connection, restarts at the right alternative quality, and well, that caused all of these ABR switches. Wasn't really what we wanted to do, but in our product, we actually have a capability that we can automatically change the latency or allow the customers to set a latency window in which the client can change the latency if it notices that the current network is not able to stream out at the latency that it's normally going to do, being as low as possible. Adding about 500 milliseconds in these bad bars, because 500 milliseconds was like the largest amount of time that we saw that, well, no packets were getting through. At some points in time, the packet loss was just so big that nothing was getting through the pipe. So increasing it with 500 milliseconds did solve the problem, but we didn't want to do that because, of course, well, we wanted to do something which was a bit better than that. Interestingly, at that point in time, we also had just wrapped up a lot of lab tests on how we could improve the protocol even further. And something that we had been testing was what happens if you start using the same protocol, which normally runs on HTTP 1.1, if you start running it on HTTP 2 and HTTP 3. HTTP 2, based on the lab trials, we noticed, well, you have TLS 1.3, 0 round-trip time handshakes. That could speed up significantly all of the connection setups that we're doing, because we were aborting connections if they were getting blocked and then restarting them. And on top of that, something that we noticed in the lab as well was when we were setting up like multi-view experiences with multiple different videos, that the way how the UDP traffic in QUIC and HTTP3, how that behaves, that actually brought benefits as well for the parallelization of the different streams. The network behavior there was significantly different, and the user experience was better as well. So we looked at it and we said, okay, let's start trying this out. And obviously, you cannot really test these kind of things in a lab. So we set up A/B tests. Certain percentage of shops. We started with the absolute worst shop that we found during the initial tests. There, we deployed the new solution, and then gradually we grow 1, 5, 10, 100 different shops. And we increased and increased and increased. And what it showed was that using HTTP3, we were actually able to get back on par with the original latency that we saw in the good shops as well. So we could not just avoid doing these ABR switches, but the connection setup, the way how the network was behaving, was actually good enough that we could, in a lot of cases, avoid needing to switch down to a lower quality, and we could keep playing at higher qualities. So we didn't have to have this additional buffer anymore. And I do have, if that works well, a very boring overview of all of these screens that we had. Some of them were set up in labs, some of them were set up in some of these bad bars where we were comparing satellite feeds, SRT feed, WebRTC feed, and then HESP at different latencies that was configured. And the stream does get more interesting a little bit after that, and especially with the frame changes, you can see how it's working. But that was it. That's basically the test that we've been doing, and quite a lot of interesting learnings that we learned out of this. So what did we actually learn out of it? And the first thing that we learned out of it is the thing that probably everybody will say, yes, we know that, and obviously we knew that as well, but it's the thing everybody always wants to forget. Everybody knows that networks are bad and that you shouldn't just test in a lab environment. But these networks, they were really, really bad. They were probably some of the worst networks that we had ever seen running the solution. And we've been running it across a lot of different locations. But this really wasn't a great network. So yes, you should be able to manage bad networks. Don't just test in a lab, but also occasionally you have to test in production and see what the actual networks are going to do. More importantly, and that was something that really did genuinely surprise me, also during our lab tests already. A lot of people always say if you just switch to HTTP2 or HTTP3, it doesn't make a huge difference if you're not using, for example, the prioritization schemes that you have in QUIC, or if you're not benefiting of the new transport mechanisms that are available there. But in our tests, we actually saw that this does make a very big difference, especially in startup times for connections. All of these things, when things go wrong, the ability to recover a lot faster, it did make a very significant difference for us. Difference even being so big that at this point in time, we're rolling out HTTP2 and HTTP3 as a standard across the product, because the difference is just quite remarkable. Not something we expected, but works extremely well. Other than that, of course, very happy to see more proof points of HESP in action. I know it's not that broadly used. It's always the betting use cases, always a lot more niche. But we were very happy with the team that we could make it work even in these these bad circumstances. And there's a lot more testing and a lot more things that we will be doing over the following months and years. We have quite an interesting track, leveraging, for example, prioritization schemes in QUIC and doing other transport. But, well, that's more work to come, more fun to have. That's about it. Questions will be during the breaks, but if there's any, feel free to come and find me, and more than happy to help and answer them.